All right, in the SL portion of waves, we've already covered diffraction, but we were talking about it in terms of interference when we were looking at the interference form between 2-point sources or two waves. We talked about speaker interference, even light interference, and we used Young's double slit equation. But in the HL section, we get a little bit more in detail as to how diffraction occurs, and you can actually get diffraction patterns like these. Okay, remember you have alternating bright spots, dark spots, bright spots, dark spots formed on a screen. You can get those diffraction patterns when you shine light from a laser that is coherent and in phase. When that light goes through an opening, just one opening, it makes a diffraction pattern, which is very strange. Okay, so that's called single-slit diffraction. All right, so just to remind us, diffraction is the apparent bending of waves around an obstacle or an opening. That wave front is going this way and the ray is showing us it's going in that direction. And for some crazy reason, that wave bends around that corner. That's why if you're sitting inside of a room, you can hear what's happening outside because the waves bend around corners. All right, we can explain why that happens using a principle called Huygens principle. And diffraction patterns can be explained by interference, which we learned in the SL section. All right, so just to remind us what the classic diffraction pattern looks like. Okay, so here's our slit, or that opening, the wave has gone through, and here would be a screen, and on that screen we would see a pattern. And I've shown you this in class, and you've seen it in the SL section, but you would see a very bright spot forming right where the hole is, and that's what we'd expect. The light would go straight through, and that should be the brightest spot. But then the strange thing that happens is you get alternating dark areas and bright areas, and the intensity of those bright spots start to weaken the further away we get from the center, which could be expected. But why do we get these dark regions? Okay, it doesn't really look like I should be getting a dark region. Why are we forming dark regions in between these bright spots? How are we generating interference when one wave is going through that opening? Shouldn't it just be spreading out and making a big white blob or a light blob, colored whatever light I'm using in that region? But here we get an actual interference pattern. Now the brightest spot in the center is called my central maximum. You need to memorize these terms. The next bright spots are called your orders. So this would be my first order maximum. That would be my second order maximum. And that would be my third order maximum because it's 3 spots away from the center. These dark spots are called minima or minimums. And this dark spot here is my first order minimum. That would be my second order, and that would be my third. Likewise over here, this is my first order minimum, second order minimum, and third order minimums. Okay, maxima are formed by constructive interference, if you remember from interference in SL, and minimums are formed by destructive interference, okay? And that occurs when waves meet up either crest to crest, that would be constructive. Destructive occurs when a wave meets out of phase, where a crest meets a trough, and that would be destructive. So these are formed by interference. So let's just try to figure that out. How can an interference pattern be made from only one wave source? It just doesn't make sense. Well, if you watch the videos that I included in the lesson, you would see a really good animation of how Huygens' principle works. And I'll just try to explain it again. I'll draw it again. But we're going to try to figure out how the diffraction pattern or that interference pattern will form on a screen over here. Okay? So when a wave that is in phase approaches a barrier, what Huygens' principle says is that all waves can be treated as many, many, many point sources. Okay, so along that wavefront, I have an infinite number of point sources that are generating waves on their own. So when that disturbance in the medium, okay, approaches here, that barrier, what it'll do is it'll disturb the point sources that are already inside that barrier. And those point sources are going to be generating waves on their own. When they get disturbed, they become point sources to generate waves. So each one of them is going to generate waves. And they're going to look like this. Now they're generating waves in phase. Okay, already I've kind of skipped one. But they're generating waves in phase. So wherever the crests overlap is going to be constructive interference. okay? And what I can see is that that region over there has a lot of overlap, okay? So that I would have very strong wave fronts traveling in that direction, okay? And those wave fronts would end up on my screen. So this is the screen, okay? They'd end up at that screen. And what I would see is a very large bright spot formed right there where the opening is. That's our central max. But why, the big question that I'm asking here is, why do I have a minimum? Remember, that's a destructive interference. That's my dark spot. Why does a minimum form? Okay, so let's go back here. I'm just going to use this red marker. Okay, if I started with this dot and I went to the center here, and I started with that dot and I went to the center here, the path length is exactly the same. All of these have a partner, a coupling partner, where the path length is exactly the same. If the path length is the same, okay, we can say that a crest is going to meet with a crest, and it's going to be constructive interference. All right, so that would explain the central maximum. We have constructive interference because all the path lengths are the same, and crests are going to meet up with crests all in that zone, and it's going to be very nice and bright because it's the path of least distance. But over here it's dark, which means I have to have destructive interference, okay? And that's based on geometry. Let's see if I can erase these. Yes. Okay, so let's take a look at that. So I'm going to use green to illustrate that. So if I travel from here and I travel from here, we can both agree, or we can all agree, that this path length is different from that path length. And that path length difference is going to be 1/2 lambda. And it just so happens that every coupling partner, if I did the math, if I did the measurements with a ruler, I would see that the path length difference for all those coupling partners is going to be 1/2 wavelength, which is going to mean that they're all going to destructively interfere when they get over here. Okay, so that's why we have a dark zone. And then you're going to have another bright zone appear over here, and another bright zone appear over here. And the math behind that would be that if I drew the lines, okay, they are different path lengths. That length is longer than that length. But in this case, the path length difference is going to be a whole wavelength difference, okay, which means that they're going to meet in phase. And if they meet in phase, it's constructive interference. So all these maxima are formed by constructive interference, where the path length difference is 0 or a whole wavelength difference. Okay, and all these minima, the minima over here, the dark zones, the path length difference is 1/2 of a wavelength. All right, we're going to do the math. I'll show you an equation in the next video where you can calculate this diffraction pattern.